Hi everybody, today we study one-dimensional motion. We first study the position. In physics, we assume that space is composed of three-dimensional Euclidean space. We first consider the one-dimensional case. Suppose that we are living on a straight line. So you'd like to denote the position of an object. To describe the position, we first introduce a reference point that is called origin. And we just use the symbol O to represent the origin. To describe a position of an object relative to the origin, we can say this x is on the right side of the origin. Sure, if we flip the direction, if we look at this one into this side, this will be the left side. So identifying a single position origin is not enough to describe the position of an object. So we have to choose either left or right. So we need to define another reference point that gives a unit, just like 1 meter or 1 step or any whatever is definite length scale, and we define an arrow that is called the basis. And we identify the basis E, a vector, so bold-faced E, and put a hat on it to represent this as a unit. Here L is the unit length. And then it's not enough. The distance from the origin to position X in general is differ from the unit length L. So this is L prime, for example. Then we define coordinate that is L prime over L. Sure, this one is a non-zero because these 2 points are different. So we write this position as a vector. So x vector is x times unit vector. Because we have a single direction, we just attach an index 1 identifying this is a single directional vector. And this x is assumed to be a real number. And either x or the unit vector must contain the length dimension. So for convenience, I can put this length inside and just treat the magnitude of E1 to be just a pure dimensionless 1 unity. This is the way to describe a vector along a straight line. That basically we are using the fact that the position vector is an element of a vector space in mathematical sense. But in mathematics, if you go far away, you're approaching infinity, and to the left, you're approaching minus infinity. In physics, nobody has ever went through to approach infinity. So we expect this model is true. So that means we assume that this is a one-dimensional Euclidean space, although we have never approached infinity. If it is a very large in comparison with the scale that are our major concern, then we just say it is infinity, and within this region, the treating the components as a real number seems to be okay, regardless of the fact there is a vector space in a mathematical sense. To us, existence or non-existence is in reality is very important. So our basic postulate is that the one dimension along a straight line is assumed to be expressed as a scalar multiple. That scalar is a real number of a unit vector. That unit vector has a certain dimension of length. All right. So a particle is an imaginary massive object. Why imaginary? Because if I describe a position of a particle, we introduce a real number that contains the dimension of length and unit vector. And in order to define such a single real number, the size, the accuracy of the number must be infinity, very accurate. That means the width of the uncertainty must not exist in mathematical sense. But in reality, it is impossible to measure the position of a particle with infinite accuracy. We do not have any ruler. For example, have you ever been able to measure the size of the electron, or the just the one half of electron size, or the 1/100th of the electron size? Is impossible. However, is for convenience, we just use real number and assume a particle exists. Right? We do not require, but we just assume for convenience. And that's very important. Okay, in the straight line, there's a unit basis vector, and this one can be chosen in either this direction or this direction. There are two choices, that's all. But in two dimensions, there are multiple ways of defining the basis vectors, but right now we are considering the one-dimensional motion, just to forget about that one. All right. The approximation of an object to the particle neglects the structure in it, no size. It is valid only if there is no rotation about its center of mass. For example, two tiny objects are connected. They can rotate. In that case, we do not say it is particle. It is a composite particle. And that we produce when they rotate, there is these additional degrees of freedom. Therefore, particle means that there is no structure. Particle is just a point. Point, if even though it is not, it does not exist at all. We just, for simplicity, we consider a particle at a single point, and we allocate a real number. To describe position, for example, a particle is at the origin, then the position of the particle is zero vector. There's a null vector, and null vector is the additive identity of linear vector space. That means if I add the zero to any vector, it does not change at all. The vector space has a linear property that is the consequence of our postulate. The directions are isotropic, and first, if we choose a single direction, just like one-dimensional case, the gap between the 0 and 1 coordinate and n plus 1, the difference should be the same. This is our assumption, translational invariance. Invariance of space. That is called homogeneousness. In mathematics, it is natural, but in physics, everything is not natural. We have to be dubious about any fact, whether it is really true or not. So we assume the space is homogeneous in one-dimensional Euclidean space, then we can make use of this kind of coordinate system. X equals E1 times real number. This one is called the Cartesian coordinate. If we extend to 3 dimensions, we have 3 basis vectors and corresponding Cartesian coordinates x, y, z. And if there is a vector x, then in opposite direction there is a minus x vector. For example, the origin, if I go forward with the equal amount, if I go backward, the corresponding vector is a minus x. So in space, in the Euclidean space, we assume then there is a position vector that has a conjugate that is just opposite direction and with equal distance from the origin. And this one behaves as an additive inverse. For example, x minus x equals 0. So null vector is an additive identity, and x minus x is the additive inverse of the sum of two position vectors. As well as we define the coordinate to define the position vector. Using this way, we can find the difference between the two positions. And the difference between the two positions is called displacement. This is the displacement. I have a straight line. There is the origin, and unit length is chosen. Then from 0 to the unit length point, we define the basis, and after that we multiply real number to identify a position vector x. In a similar manner, I have another point x prime. Then what is the difference between that? From x to x prime is defined by difference. Original and final, the initial and final. The difference is just a vector connecting the starting point, that's called the tail, and ends up with the end point, there's a head. If we make use of the Cartesian coordinates, because there is a single basis, so we can factor the basis out, and the coordinate of the resultant vector for the displacement vector is x prime minus x. This is the coordinate for the resultant vector representing the displacement. As I told you in the previous page, we assume the homogeneity of space. That means the unit vector from 0 to 1 and n to n plus 1 for any n. or x to x plus 1, in any case, the distance should be the same. That is a basic postulate of physics if we when we employ the Euclidean geometry for our space. Another important assumption, even though right now we are studying the one-dimensional case, if we extend to the two or three-dimensional case, such a homogeneity is valid to any direction. That is called isotropy. So left, right, isotropic, up and down, isotropic. Next we consider distance. Distance is the magnitude of the displacement. 2 points. We can define a line segment, and there's a point vector A, and there's point vector V, and any point in here between A and B can be parameterized by A plus T B minus A. We know this vector from A to B is just defined by B minus A. As a result, this one, when we substitute t equals 0, this one vanishes, the starting point. When we substitute t equals 1, it becomes a b, so endpoint. If we increase a t greater than 1, then it will be extended to the right side. If we choose t less than 0, then it can extend to the left. So in this case, this one can be chosen as the B minus A can be chosen as the basis instead of E1 hat, but this one has a non-unity magnitude for the length, so it is better to rescale it to have a unit length. Anyway, this one is a basis, and this A can be replaced with the origin, so a kind of reference point. Anyway, in one dimension, the distance is just this length of the vector. So distance is defined by making use of the scalar product, and in one dimension, scalar product is either the two. We have x vector and y vector. When they are parallel, scalar product of x and y is just the product of the magnitude. And if they are parallel, if they are anti-parallel, so opposite direction, the scalar product is defined by, so it is a positive and it is a negative. And when either one is vanishing, the scalar product becomes 0. In such a manner, I can define x vector square is x dot x. And actually, based on this definition, it is just x vector's magnitude square. So if I put the square root of it, why I end up with the fact it is x vector magnitude. So that is the distance. Distance is a scalar. The magnitude of a vector is chosen in this way. So we just replace this one by displacement. X prime minus x, the displacement from x to x prime. In that case, I can substitute this one into this formula to find out the magnitude of delta x. There's a displacement magnitude of the displacement, that is distance, is the square root of x prime minus x squared, and actually that is on the axis, just coordinate x this to this. These are real numbers, coordinate. If I can express this one as the difference in the coordinates and absolute value. Next, we consider average velocity. Average velocity, okay, there's position. Position changes, so this is displacement. If, if there is a displacement, what is delta t? How long does it take to make such a displacement? Then the ratio of displacement to spend time, elapsed time, that is called velocity. And if it is finite, then we call it average velocity. If I take the limit at delta t goes to 0, very small time period, then it becomes instantaneous velocity. As far as the average velocity is concerned, the magnitude of the average velocity is called average speed. Let us consider this case. There are three paths. Three objects starts to move from A following three different paths, and they arrive at the same position B at the same time, t equals t, and t equals capital T, and t equals 0. We are interested in to find out the velocity. Velocity equals the displacement over delta t. Delta t right now is t, right? For a given delta t, all of the object has the same displacement, xb vector minus xa over t. So all of the three objects have the identical velocity. However, this is average velocity. If I want to find the average speed, numerator is replaced. This displacement is replaced with the distance. T is the same. We know it is trivial. This is shortest, longer, the longest. Therefore, denominators are identical, but three distances are different. So long, short. So this one is a fast. This one is the slowest. And this one is medium, as far as the speed is concerned. Okay, let us consider the motion of constant velocity. This horizontal axis is time, and vertical axis is displacement. And we find the slope is constant. So for any given delta t, the displacement delta x, the ratio is a constant. So the slope is constant. We find the displacement is a sum of some specific position at a certain time, t equals 0, and added number is a v0t. Any number in physics can be added only if they are of equal dimensions. So v0t, its dimension, and x0, they must be of equal dimensions. So velocity is dimension, time, and length. So velocity has the dimension of length over time. Next, we consider two paths, two objects. One is following a sine something, and the other follows a parabolic curve. Okay, the sine and the sinusoidal function has argument. For example, it says just number. This is sine x. Sine x varies. This is 0, while maximum is 1 and minimum is -1. The sine of x is a scaleless function, and as you might have expected, this x is dimensionless too. At the end of this lecture, we'll find the sine x can be expanded in power series as we call it Taylor series expansion, this kind of form. Any number with different power can be added only if they are dimensionless. So we think this one is dimensionless, and the sine function is dimensionless, and we have this position x1. So this one has dimension of length. Because this one is the sine function is dimensionless, a has the dimension of length. In addition, because 2 pi is dimensionless and time has dimension of time, this one is dimensionless. So length, time, and mass, they're all those powers should be 0. So because it's a time, t has a time dimension, we have a c. As a result, we find that the dimension of c is a time. Only if it has same power, they cancel to have dimensionless number. As a result, c is a constant of dimension time. Next, here, this one, c is she has the dimension of time. The t over c is dimensionless. Dimensionless number can be added to a pure number, so this one is dimensionless. And then we have a b times a t, and we have x2 as dimension of length. B has some dimension and t has dimension of time. Therefore, dimension of b is length over time. That is dimension of velocity or dimension of speed. All right, the x1 is illustrated as a red curve, and x2 is illustrated in a blue curve. During the time interval 0c, the displacement x I c, this is c, subtracted by xi 0. Okay, originally both objects were x2 0, both of them were 0, and x1c, x2c, both of them are 0. Therefore, the displacement is 0 for both paths. Average velocity of each particle, because the displacement is 0, average velocity is 0. Average speed, if I want to know the speed, then we have to know the distance of travel. Here, A, this is A, and A has this is maximum value is A. Alright, this amount is A. And then it traveled all the way through minus A, so this distance is 2A. And then it rises up, end up with a 0, so A. So the total distance of travel for the red curve is A to A plus A, or 4A. And the speed is 4A, distance divided by time. This one will be the average speed of the red curve object. In this case, the blue curve began with a 0 and maximum value is at 1/2 c. So we substitute 1/2 c. B 1/2 c 1 minus 1/2 c c. So it's bc over 4. 1/4 of b times c. That is the total distance of travel from 0 to 1/2. So you need to, this is bc over 4, the bc, 1/4 of bc. If we add them together, then the total displacement is 1/2 of bc. And then what is the time? This time is c. So the average speed is 1/2 of b. Sure, this plus shows that A and B are positive, so I did not put any absolute sign on it. Next, we consider the velocity and speed. If we know the displacement, then we can compute the average velocity and average speed. In case we take the limit of time difference to measure the displacement goes to 0, then we can obtain the instantaneous velocity. And the magnitude of the instantaneous velocity will be the slope. The sign determines if the sign is positive, then velocity increases. The sign is negative, velocity decreases. So deceleration or acceleration. Instantaneous speed is identical to the instantaneous velocity, except that if the speed is a positive definite. We have listed 5 simple functions, and you're asked to compute the physical dimensions of constants. We already have done a lot of work for how to identify the dimension of constants. The basic idea is if some numbers are added, then all those numbers must be of equal dimensions. This is a simple function, sum of functions. If I take the derivative to find out the velocity, I need to take the derivative f of x, f of t, and g of t, and take the derivative of sum of functions is just the sum of derivatives. So it is awkward to write this differential operator too many times, so we usually use dot. X dot means time derivative of x. So follow the same rule to find out the dimensions of those constants. In case we have product, we need to find out the derivative of product. For example, A times B, derivative is AT plus delta T, B T plus delta T minus AT BT, and divided by 1 over delta T, multiplied by 1 over delta T. So we can reorganize this expression as a T plus delta T minus AT factored with the T plus delta T. And then because we have subtracted this amount, we need to add this one. A of T, if I add, is B plus T plus delta T, and then subtract B of T. Now we divide this one with the delta T, then this one becomes A's derivative, and the limit delta T goes to 0, this one becomes B of T. In a similar manner, this one becomes the derivative of B, and this one is A of T. So in this way, we take the limit to find that this is A derivative B and AB derivative. So this is called Leibniz rule for taking the derivative of product function. If we apply this one twice, we can find the derivative rule for 3 factors. For example, this one AB times C is derivative. So I need to find out the derivative of AB, C, and AB times derivative of C. If I substitute this result, it is A dot B plus AB dot C plus ABC dot. Finally, we end up with this result. For example, if I have all these are equal to A, then derivative of AQ is 3 times A squared A dot. So this is a simple chain rule. That means this one is take the derivative with respect to A and take the derivative of A with respect to T. So this is 3A squared and A dot. So in a similar manner, we can extend this formula to have arbitrary vectors. So n vectors, then we can put dot one by one. In this way, we can extend this idea to derivative A to the n is n A to the n minus 1 and A dot. This is again the chain rule. So we can make use of these formulas to compute the velocity, instantaneous velocity, and if we repeat the time derivative one more time, then you'll end up with the acceleration. Then acceleration in the same manner, the average acceleration is defined for a finite time interval, and instantaneous acceleration is defined by taking the limit as delta t goes to 0. And again, dot of something is time derivative of something. And double dot means the double time derivative. Okay? We have seen a single first order time derivative of product functions. This method can be extended to the double time derivative. For example, A dot, what's that? This one is A dot B plus AB dot. What is AB dot dot? That is AB dot N dot. and AB dot equals A dot B, AB dot, and then dot. That is A double dot B dot, A dot B dot, A dot B dot plus AB dot dot. That means we have two common terms. We have double dot A B. Wait a second. Wait a second. This one should be removed. Plus 2 times A dot B dot plus AB dot dot. This is the answer. Again, this one can be repeatedly applied to find out the nth order derivative of product function. This is a binomial factor. This is, we usually use a combination NCK, n factorial, the permutation of same kinds. If I have this derivative applied to A of the same kind, so we have k factorial, derivative n minus k derivatives applied to B has the verticalities of n minus k factorial. So this combination factor is a binomial factor. Binomial factor. Binomial factor comes from the a plus b to the n is n factorial, k factorial, n minus k factorial, a to the k, b to the n minus k, and maximize sum over k from 0 to n. So these coefficient appears in the binomial expansion. That's the reason why we call binomial factor. In a similar manner, we can extend this one to many factors that can be, for example, A, B, C, D, E, F, G, H, I, J, K, element of B, Q, R, S, T, until Z, and further, whatever. Then the sum is n factorial, k1 factorial, k2 factorial, and k z, okay, z, k a factorial, k b factorial, k z factorial. And there is a restriction, then sum of any k's is n. Okay, and then this is a to the k1, b to the k, ka, b to the k, b, c to the kc, z to the kz, something like that. So because they are two terms, so we use the binomial expansion. We have multiple terms of the multinomial factor. Okay, this kind of a generalization is quite straightforward, and it is just wash your mind, wash your brain, and just follow the route, just step by step, repeatedly. To prove this, we use a mathematical induction. A very straightforward and absent-minded way. Don't think about, just forget about anything and be stupid as possible. Just n equals 1 is an integer, and 2 is integer, 3 is integer. How? You just add 1 by 1. If 3 is integer, then just add 1, then you have 4 integer. And then add 1 to 5. Anyone can do this. So just to do this for the initial value, and suppose that we have found that a certain k, you still have the same rule. Then you find what you have to find out is just substitute k and add one more piece to find out that the rule is invariant for just by replacing k by k plus 1. Then you end up with the fact that any integer can be determined as a set. One is an integer, and if something is an integer, you just add one, you still have integer. So this is how to generate the whole set of integer. So this is called mathematical induction. Very, very stupid way, but very, very efficient way. So it is a very simple problem. It looks very complicated, but this is a very simple formula. Okay, so anyway, this kind of derivative rule is called the Leibniz rule. And this kind of writing down the derivative is called the Leibniz notation. The use of primes is a Newtonian notation, and in many cases, for simple cases, the Newtonian notation is better, but at higher order, how can you find out the count number of dots? How many? Are there 8 or 10, 11? Very difficult to write down, but it is very easy to write down. So in many cases, people prefer the Leibniz notation to Newtonian notation. So repeat taking the derivative once again to find out the acceleration. A special case of acceleration is called the constant acceleration. That is usually, we usually know that the constant acceleration is due to the gravitational acceleration near the surface of the Earth. Sure, if the altitude is much increases, the acceleration decreases. However, near the surface of the Earth, because the radius of the Earth is very large, and if the acceleration is not large enough, the damping or the resistance of air can be negligible. In that case, the acceleration gives the power law. That means the acceleration is constant acceleration. What you do to find the velocity, because a is constant, at plus something, the velocity at t equals 0. If you integrate this formula one more time, then you have x of t, you have x of 0 as the initial condition, and remaining piece is x of v0t, and this one becomes 1/2 at squared. So this formula gives a constant acceleration, displacement for the constant acceleration. So if you write down the xt dependence, time dependence of displacement, it becomes either in this kind of form or this kind of form. It's probably curve. If you take the derivative, the second order, this degree 2 becomes the degree 1, it becomes line. And the slope of this line is determined by the acceleration. So Vt subtracted by V0 equals At, and acceleration is Vt minus V0 divided by T. Okay? This acceleration slope is everywhere the slope is the same. If I apply this fact between two time, T1 and T2, then we have V1 and V2. Line is called the line. Adjective is a linear relation. The midpoint between the time is midpoint between the two, the initial and final velocity. So if you connect these two, you still have a point that is on the single straight line. There is a simple formula to find out the area. An elementary school student can compute the area of a trapezoid. Trapezoid area of a trapezoid, it is difficult to calculate. No, just copy this one, copy, copy, copy this one to have double, flip the direction by reflection, reflection twice, so point like symmetry. This point becomes, if this one goes up, so flipped and combine. Then you end up with the doubled area. And then everyone can measure this area. This height is T2 minus T1 is identical. And the width is just sum of these two sides, is V1 and V2, because this one is a copy of this one, and this one is copy. So this side, V1 plus V2. Very simple. So area V times dt. This is area. This is the displacement. Okay. This displacement is the area. This area, that area divided by 2. So 1/2 of this large rectangle is the area displacement. All right. This side V1 plus V2 is in here, and this side T2 minus T1 is in here. We have to multiply 1/2. Wait a second. The rate V2 minus V1, this rate of changing T2 minus T1 this is acceleration. All right. So V2 minus V1 is what? All right. This one gives a T2 minus T1 equals V2 minus V1 divided by A. All right, we have denominator A and V1 plus V2, V minus V2. So middle school students can expand this to find a V2 square subtracted by V1 square. This is the displacement. Actually, if we multiply A to in here, displacement A, so 1/2 V2 squared minus V1 squared. Well, why don't we multiply mass? Then MA delta X equals to 1/2 M V2 squared minus V1 squared. What's that? This is the difference of the kinetic energy, and this is the work. Force times displacement is work. So actually this is the Coriolis work kinetic energy theorem in a specific case for the constant acceleration. Free fall acceleration is just the case with when we replace G with the A with the G G is toward the ground of the Earth, and magnitude is 9.8. It is not an absolute value. It depends on the soil structure, the weight, the density of the soil near the surface, and the altitude of the position, and so on. In the graphical analysis, this is average velocity for a finite time difference. And if we change the difference of time to 0, then you will find this a kind of slope that is tangent. This straight line is tangent to the curve. Sure, if it is possible to have this kind of shape of x, that means a left velocity and right velocity near this cusp are different. So we can take the derivative on either side, but the two derivatives are different. This one really happens in reality. If you bounce a ball against the rigid wall, the velocity just before touching the wall, it is a negative. And right after touching the wall, it bounces back and becomes a positive. So at some point, just before and after, there's abrupt change. There is a discontinuity of the velocity. And if we count the area under the curve, then you will find that that is equal to the definite integral between 2 points. If the curve is a positive, it is a changing in positive sense. If the area is under the time axis, that change should be negative. So in this case, our value is v, and the integral becomes the delta x, that is for the displacement. If we have acceleration in the vertical axis, then it will be the change in the velocity, like this. All right. In the previous pages, we have considered the Leibniz formula for the derivative of product function for multiple derivatives. So why don't you make use of that mathematical induction to find out that it really is. And just before we here, I have already told you it is possible to have there is a discontinuity in the velocity, and think about it. It if it is really true. I mean, when something is changing its velocity, to have left limit of velocity to be negative and the right limit of the velocity to be positive. And is it true? Or for example, the time gap of the before and after can be arbitrarily small, just like mathematician can imagine. In that case, the acceleration becomes infinity. If the acceleration is infinity and mass is finite, sure, a mass of a ball is a finite value. It is not an infinitesimal value. We cannot decrease the mass of the ball. In that case, mass times acceleration, and acceleration becomes infinity, then mass times acceleration is force, and force becomes infinity. Is it possible to have force to be infinity? Not at all. It is impossible to have force infinity. And actually, from this kind of physical situation, the mathematician didn't understand very much at the very beginning. We have a physicist called Dirac, that we have the Dirac delta function that is a kind of distribution. Now they say Dirac delta function is a distribution, but in comparison with the mathematicians who are very rigorous about solving mathematical problem, physicists are not rigorous at all, because our main goal is to solve the natural problem. No, we are not to solve the mathematical problem. Mathematical problem is absolutely independent of physical problem, because physics is a physics. The physics is based on nature. Mathematics doesn't have to be equal to nature. Absolutely not. So, from this kind of problem, you will notice how to resolve any problem of infinity or absurd singularity that appears in physics problem. It is not mathematics. You should know how to solve that kind of a very strange way to solve problem. Mathematician that cannot solve that kind of problem at all. Later, once a physicist find the real solution based on cheating, physicists always cheat, because we can cheat because the solution exists in nature. But mathematician cannot find a solution at all from such kind of ill-defined problem. Mathematician can solve problem that is mathematically well defined. For physicists, the physics problem is very dirty, and there is no reason why we stick to mathematics. That's the it looks mathematics is very similar to physics, but absolutely not. You should learn through this course that physics is a very interesting and mathematics is also interesting, but physics deals with nature. Thank you.